Let's consider the isothermal hydro equations in the absence of body forces, so there is no extra acceleration in the momentum equation. So we have the density and the velocity and a pressure. These are three variables, but only two equations. To close the system, we need an equation of state, which is going to relate the pressure to the other quantities of the problem. We will use the ideal gas law, so that the pressure is the density times the square of the sound speed over gamma, the adiabatic index. And for isothermal gas, we're going to use gamma equal 1. Now consider a one-dimensional configuration so that the velocity has only one component, u. The equations then become in one-dimensional form, this set of simpler equations. So this system might emit waves. To find the waves, let us linearize the system, decomposing it into phase and perturbation. That means that for any quantity q, be that the density or the velocity, we're going to decompose it into a base state, q bar, and a perturbation, q prime. We can plug this decomposition back into the quantities for both density and velocity, and the equations are expressed in this form. At first, this looks more complicated, but we can consider now that the base state is constant. So its derivatives, the derivatives of the barred quantity, are going to cancel. So canceling here the bar term in the density, the bar term in the velocity, and in both the time and the spatial derivatives, these are the equations that we get. Now consider also that the system is Galilean invariant, so that we can set the u bar equals 0. Even if the system is moving with u bar not equal 0, we can do a Galilean transformation to follow the system, changing the reference frame. So we can write the equations then without the u bar term, and this is what we get. We can now consider that the base state of the density is much, much larger than its perturbation. Now we can do the first approximation. So far, this is exact. What we did was that we decomposed a quantity into something that is not changing and something that is changing. That's not an approximation, that's simply a decomposition. And here, we didn't do an approximation either, we just did a Galilean transformation. Now we do an approximation to say that the base state of the density is much, much larger than the perturbation. That means that the system is only weakly compressible. With that, we can ignore the prime terms in the right-hand side, leading to these equations. Now, this equation still is impossible to solve because we have this nonlinear term in here. But notice that the two quantities are primed. And we said that the prime quantity is much, much less than the base state. So this prime quantity, we can treat them as infinitesimals. And these are two infinitesimals. So this is a second order term. It's much smaller than the first order term that we have here and here, which only have one primed quantity. So two prime quantities are of second order and ignored, canceling this nonlinear term. The system then becomes this much simpler set of equations. So we can use this now to find the wave solution.